While we can calculate a moment about any point, it is far more useful to know how much of that moment produces a rotation about an axis where such rotation is possible. The easiest way to think about this is the simple act of opening a door. For illustration, suppose the door has a knob and you have to grab it and pull it toward you to open it. You've done this hundreds of times and never given it a thought. When you grab the knob, you more or less pull in a direction perpendicular to the plane of the door. This maximizes the moment about the hinged axis and makes it relatively easy to open the door with a modest force. We want to formalize the process for finding what we will call m sub h or m sub l, the projection of the moment along the hinged axis or about a line. As with our calculation of the moment about a point, there will be something called a scalar approach and something called a vector approach. I would again advise you to use the vector approach in 3D problems because it can be very difficult to see relevant distances in a problem with arbitrary orientation in 3D. The vector approach requires one additional step beyond taking a moment about a point. We can summarize the procedure this way. First, pick any point along the axis for taking moments. Second, evaluate the moment about that point as m equals r cross f. And then finally, the new step is to take the dot product between the unit vector along the hinged axis and this moment to get m sub h. So we'll write m sub h is equal to the unit vector along the hinged axis dotted into r cross f. The scalar approach is more visual. It requires identification of a point on the line of action of the force in addition to the hinged axis. The hinged axis, a line, and the point on the force's line of action defines a plane. We then proceed as follows. First, we resolve the force into components parallel and perpendicular to this plane. Second, we observe that the parallel component has a line of action that either intersects the line defining the hinge or is parallel to the hinged axis. In either case, the only contribution to a moment about a point on the hinged axis is perpendicular to the axis itself, so there is no projection of this component along the hinge's axis. That means the moment about the hinged axis is then due entirely to the perpendicular force component. As long as we can identify the perpendicular distance d between the hinged axis and the perpendicular force component, we can identify mh as the perpendicular force component times that distance d. If this sounds like a lot of words, let's take a look at an example and try to make more sense out of it. In this first example, a person is trying to tear a piece of cardboard along the axis AB. If it seems a stretch to think that this could be done easily with cardboard, imagine instead that it's tissue paper or gift wrap. Even though axis AB isn't a hinge, the moment about that axis will contribute to tearing along AB, and we'd like to know the magnitude of this twisting load along that axis. The axis AB lies in the xy plane, and the force applied at C is parallel to the xz plane. As this is a 3D problem, we'll begin first with a vector solution. We begin by picking a point on the axis AB for taking moments. Two candidate points are shown here, A and B. The relative position vectors RAB, RAC, and RBC are all shown in the figure, as well as the force F. For the first solution, we begin by taking moments about A, then dotting that result into a unit vector pointing along AB. Given that RAC just lies along the y-axis, we have this result for the moment about A. In the I direction, we simply have 24 centimeters times minus 16 newtons, which gives us the minus 384 newton centimeters along I. We have no contribution from J because of the zeros at these two locations. And then in the K direction, we have 0 minus 12 times 24, or minus 288 Newton centimeters. So our moment about A consists of a component in I and a component in K. We then dot that result into a unit vector pointing along AB, and in this case we've left the unit vector as the relative position vector from A to B divided by its own magnitude. We can see that that has a component in I and a component in J, and so the only result that will survive from that dot product are the dots of the two I components into each other, and that ends up giving us minus 384 Newton centimeters times the ratio of minus 30 to 31.05. That gives us a result of plus 371 Newton centimeters. Note that we could have defined the unit vector from B to A instead of from A to B, in which case our result would have had the opposite sign, but this produces the same result, a moment of magnitude 371 Newton centimeters and directed from A to B. The second solution is shown here, and we begin by taking moments about B. Note that the moment about B is not the same as the moment about A. In fact, in this case, we have non-zero components in each of the I, J, and K directions. That said, when we evaluate the projection of that moment along the axis AB, we get the same result that we had in our first solution. Finally, we note that this calculation represents one application of the scalar triple product. Even though we can write the dot product in either direction, it doesn't matter whether we write A dot B or B dot A. Typically what we would do here is put the unit vector in front, since that's going to occupy the top row of the mixed triple product. So more often we'll write it like this, where then the unit vector, the position vector, and the force vector occupy the first, second, and third rows respectively in the mixed triple product. This is a way of just combining all this into a single step, and once again we get our result of 371 Newton centimeters. A summary of the steps involved in using the vector approach is given here. A couple of points to highlight. First, we need to pick a point on the line for taking moments. Often, as in the previous illustration, there will be more than one obvious choice. The moment is likely to be different at every point, but the projection of that moment along the axis of interest will be the same. Choose a point that is convenient for taking the moment. Second, once we have calculated the moment, we need to dot the result into a unit vector pointing along the line or hinge of interest. There are always two possible choices for this unit vector, one being the negative of the other. There often isn't a strong reason for choosing one over the other, but it won't matter for the result. A positive value in one direction is the same as the negative value in the opposite direction. Elements of the scalar solution to the same problem are shown here. We begin by defining a plane from the hinge or line of interest and a point on the line of action of the force. In this case, the point is where the cardboard is being gripped at C. So the plane that's defined from the hinge and that point is coincident with the cardboard itself. We then resolve the force into components parallel and perpendicular to this plane. The force component F parallel makes no contribution to a moment about the hinged axis. To see this, recall that we have the flexibility to pick any point we like on the axis for taking moments. Suppose I extend AB backwards in this direction, and then pick a point where the line of action of F parallel intersects line AB. If I call this point of intersection D, then RDC cross F parallel is 0 because RDC and F parallel are in fact parallel. The projection of a 0 vector onto the line AB is obviously 0. If I had picked a different point, let's call it E, then REC cross F parallel isn't 0, but since REC and F parallel both lie in the xy plane, the cross product that results will be purely in the z direction. The projection of a vector in the z direction onto the xy plane is also 0. This leaves us with the remaining force component, F perp. To get the value of the moment about AB due to F perp, we need to identify the perpendicular distance d shown in the figure. Note that this distance is along a line perpendicular both to F perp and to the hinged axis. This also illustrates why this scalar approach is not generally recommended in three-dimensional problems. Even though we can see where d is located, calculating its magnitude could be difficult in an arbitrary orientation in three-dimensional space. In the present problem, though, d is also in the xy plane, and that makes its calculation simple enough for us to find it. Here we are looking at the cardboard from above the xy plane, and we can see that triangles ACE and ABD are similar triangles. In particular, these small acute angles are identical, which means their cosines are identical. Setting the cosines, the adjacent sides over the hypotenuse, equal to one another allows us to find d as 23.19 centimeters. The moment magnitude about axis AB is then F perp times d, which is 16 newtons times 23.19 centimeters, which is again 371 newton centimeters. We could then go back to the previous slide to determine the direction of this moment. Using the right-hand rule, we can use this position vector and cross it into F perp. And the sense of that moment will be going from A to B. A summary of the process for finding the moment about a line using the scalar approach is given here. Again, the trickiest part of this process can be identifying the moment arm, which is perpendicular to both the perpendicular force component and the line defining the hinge or axis of interest. Because finding d can be difficult, we can sometimes use the equivalence of the vector and scalar approaches to infer d. That is, we can use the vector approach to calculate the moment about the axis, MAB here. Then, since this result is equivalent to F perp d, we can infer d from the ratio of the magnitude of the moment about the hinged axis to the magnitude of F perp. We close this section with the following example where we are trying to orient a television screen for ease of viewing. This is a 3D problem, so we will make no attempt to use the scalar approach. We will look at two different solutions using the vector approach. This second example is a variation on problems 446 and 447 in your textbook. Line AB lies in the YZ plane, and we can calculate the relative position vector from A to B as RB minus RA, and that result is 2J plus 1K foot. The magnitude of RAB ends up just being equal to the square root of 5 feet. And so the unit vector that points along AB is RAB over its own magnitude, and that ends up being 2 over root 5 in the J direction plus 1 over root 5 in the K direction. The moment about AB could be written as UAB dotted into one of two expressions, either RAD cross F or UAB dotted into RBD cross F. And we can again see from the coordinates given that we could write expressions for RAD and RBD, and they look very similar. RAD is minus 2I plus J plus 0.5 K feet. And RBD has the same numerical values as our AD, but some of the signs are changed. This ends up being minus 2I minus J minus 0.5 K feet. So I will choose to evaluate this using the mixed triple product. MAB is, again, the unit vector dotted first into RAD cross F, and that will have these components. The components of the unit vector are 0 in I, 2 over root 5 in J, and 1 over root 5 in K. And the position vector RAD has values minus 2, 1, 0.5. That's got units of feet. And the force is 0, 0, minus 5 pounds. Let's just make a note that the only non-zero contribution we're going to get is going to come from this term. We'll have our first term will be 0 times 1 times minus 5 minus 0. So we get nothing from the term that normally occupies where the I unit vector is. The second term will be minus 2 over root 5 times this cross product. And that will end up being the only term that contributes, because the last term is 1 over root 5 times essentially 0 minus 0. So what we end up with here is minus 2 over root 5 times 10, or minus 20 over root 5, which is minus 8.94 foot-pounds. Now we'll just notice that we could go ahead and carry out the calculation with the other position vector RBD cross F, but if we think about what changes in that case, it would change the sign here and the sign here, but neither one of those terms contributes to the moment about AB, so we don't really even have to go through the process of carrying out the second mixed triple product. We're going to get still a minus 8.94 foot-pounds. And the fact that this is negative tells us that the direction of this actually goes from B towards A instead of A towards B.